Hi, welcome to 10.10, Electricity at Home. Everything we've talked about so far has been what's called direct current. And that's where, we generate electricity in whatever way we do, through a battery or whatever it is. And then that electricity flows from that battery in a circuit in one single direction. It flows like, a river or something, Whereas the way we get electricity to our home is a little bit more complicated than that. It's used something called alternating current, and we're going to talk about that in this video. So, this is a diagram of a coal power plant, right? So we get some coal, we break it up into small pieces, crush it even further, drop it into a fire, it burns. And this way we're turning the energy that's inherent in the coal, we're burning it, and we lose a lot as heat and whatever else. But that heat also heats up this coil of water. The water turns to steam, and the steam turns some turbines, and that turbines turn this generator that generates electricity, and that generates electricity is sent off along cables throughout our lovely countryside, and turns on computers and powers iPads, etc. Okay, well that's all very understandable. Burning coal and turning water into a gas, and then turning a turbine, whatever. What's happening in here? This is what's interesting. So this is the difficult bit. What is it? Why does something turning create electricity? And this is what we're going to look at now. Okay, so it's called alternating current. Okay, and the way it works is that we have two big magnets here, a north pole and a south pole, and the generator turns this this rod. Okay, imagine this is a wire or a rod. Okay, and it spins it around and round and round in circles, and you can see it kind of here. So at one point the wire is kind of flat, and then it's kind of on an angle, and then it's slowly spinning around in circles. All right, and as it spins, the electrons in this wire are being attracted in different ways. All right. So when it's flat, there's an equal attraction from the North Pole and the South Pole. All right, but when it's straight up and down like it is here, you can see that there's a lot more attraction towards the North Pole. And then when it's flat, again, equal attraction. And then when it's pointing the other way, there's more of an attraction towards the South Pole. All right, and it spins around and round and round in circles. All right, spins around and round and round in circles, and as it does, the voltage changes. All right, from positive to negative. All right, so the voltage being the energy that's inherent in the electrons, it changes from positive to negative, positive to negative, or it swings back and forth anyway. And I want to explain this, and it's reasonably explainable in regards to a water analogy. Imagine you had a big pipe full of water, okay, and you had this little turbine here, and this turbine was pushing this little piston back and forth. All right, so as the piston moves this way, the water's going to rush around that way. All right, but as the piston goes back out, it's going to rush back the other way, isn't it? All right, so as the piston moves back and forth, the water is going to move back and forth like this, yeah? So it's going to move back and forth like this, back and forth, back and forth, back and forth. And you'll notice as it goes through some kind of resistor, it will resist even regardless of which direction it goes. Okay, so the water moves back and forth, all right? We have the movement of electrons, and we have, if we put like a resistor, or even, if it was electricity, for example, put a light in here, we would be getting, electrons moving through the light bulb, and we would be getting electricity, heating up that filament, and we'd get light coming out with alternating current. Now, here's the issue. Here's the thing. Why do we do this? Why don't we just get batteries and huge batteries and power everything that we need through that way, or through direct current. All right, here's the water analogy on direct current. Imagine you had this big kind of tank, and there was a tube, and out came all the electricity. Okay, or the water, or whatever it is we're using at the moment. So this tank, slowly empties, and the electrons have to travel the entire distance in order to get to your home. So if we had a power plant in central Victoria, and we wanted to light a light bulb in the Docklands, the electrons would have to travel the entire distance in order to light that light bulb. All right. However, with alternating current, they don't. All right. The current moves back and forth. Okay. And the electrons, don't have to move the entire way to the resistor, or to imagine that's a light bulb. It only has to move back and forth, which moves all this water back and forth. Okay. So there's less loss, I suppose. If the water had to flow all the way around here, it'd get lost. It'd get, it'd move out through, leaks and all these kind of things. That can happen, even in electrical wires. It's a much more efficient way of having electricity being transported long distances. The only issue is that it's awfully dangerous. It tends to come out as like 240 volts. If we did have a light bulb here, it would absolutely blow, unless it was gigantic. All right, it's really, really dangerous stuff. And I'm going to show you a video of an electrocuted elephant, maybe, hopefully. That big discussions. But anyway, I'll talk about it in class. So it's a little bit dangerous. So what we want to do is we want to convert the alternating current and have like a direct current coming out for our bits and pieces. Okay, and that's really what we do. If we can imagine this pipe kind of leading into here, and the alternating current moving back and forth, and every now and then it's siphoning off onto our power packs, which lead to iPads and whatever else. Okay. So that's how that works. Rotating wire around a north and south pole that moves the electrons back and forth on this wire. Okay, that allows electricity to be passed back and forth on this wire all the way, hundreds of kilometers to your home. Right. Okay. This is a bit of a distraction, but here we are. So have you ever wondered why, if you touch one of these metal wires, you don't get electrocuted? Okay, basically this third pin here is basically an earthing socket, right? So in the power plug, the third hole is basically connects to a metal rod that goes into the earth, and that's what completes the circuit, rather than your body being used to complete the circuit through the ground. Alright, so in the plugs that have 3 pins on it, the third pin is basically to earth the electricity, so it doesn't go through your body. However, we do have ones with 2 pins. That doesn't mean that they're more dangerous. They're actually double insulated, so that they're safe to use as well. So, that's the third pin. Big power packs. You've probably seen these. A lot of electrical devices, or some electrical devices, don't require the 240 volts that comes out of power points, and they use this little transformer to step down the voltage. Okay. Finally, safety switches. These are switches that basically they detect the amount of voltage running through amount of current. That runs through an environment, and if we are pulling too much electricity out of the mains, there's too much current running into our house. these switches will turn off, and we'll have to, go unplug some things and then turn them back on again. Okay, so that's kind of where we are on that. 10.10, I would like you to go through and put the blue words into Quizlet, and you can answer questions 1 to 6, and I'll see you in class.